We're going to switch gears here and talk about the opposite end of the spectrum in terms of pH. And we're going to talk about calcareous soils. So these are soils that have pH values above 7 or 7.2. So these are soils that contain free lime, native, natural free lime in the soil or in the soil surface. It could be in the soil or in the soil surface. If we're talking about trying to reduce the pH of a soil, we're talking about free lime in the soil surface. So where do you find these soils? Typically, you find these in arid and semi-arid regions. Precipitation is less than about 20 inches per year. The soil pH is above 7.2 and it's buffered. All right, so you learned about buffers. It's buffered by calcium carbonate or some other liming material that's present in the system. Oftentimes, in fact, most often it's calcium carbonate. And calcium carbonate in these soils can range from anywhere between 0.1 and 40%, which is a huge range. And I can tell you that even at 0.1 or even at 40% free calcium carbonate in the soil surface, the pH of that soil may be above 8. So when you have a high pH soil, the availability of some micronutrients, specifically iron and zinc, is reduced at those high pH values. In fact, when we get to those units, the micronutrient units, and specifically iron and zinc, when we see deficiencies in calcareous acidic soils, oftentimes it's with either iron and or zinc, FYI. And at high pH values, phosphorus precipitates as calcium phosphates. And this all ties back in to, well, let me get to what it ties back into in a second. Let me talk about this graph here. So here's rainfall on the x-axis and depth in inches or centimeters. And this is what you typically see. All these white dots are free calcium carbonate. And as rainfall increases, the amount of free calcium carbonate in the soil surface decreases, but it increases with depth. And so this is what happens with natural weathering. In soils that don't receive a lot of rainfall, oftentimes what you find in the soil surface is primary minerals, like primary calcium carbonate. These are minerals that were initially present when the soil formed. As weathering occurs, those forms of calcium carbonate dissolve and are moved down and reprecipitate as secondary calcium carbonates. It's almost impossible to tell the difference between the two, but that's the natural weathering scheme. And so as greater and greater amounts of rainfall occur, that calcium carbonate in the soil surface is dissolved, precipitated, dissolved, precipitated, dissolved, precipitated, and eventually it's washed out or leached out of our soils completely in highly weathered systems like you find on the eastern coast of the United States. So let me go back to the availability of micronutrients and phosphorus. And that all ties in with this figure. It's a little bit different than what I showed you earlier in one of the other units. But if you look at, say, copper and zinc and iron as a function of pH on the x-axis, as soil pH increases from above 7.2 to 8, iron availability decreases, copper and zinc decreases. Where's phosphorus? Here's phosphorus. There's a pinch off point, and then it is highly unavailable in the range where we grow most of our plants in calcareous systems, which is between about 7.2 and about 8.4. Right? Above 8.4, we're not growing plants, to be honest with you. So who cares about this opening back up after 8.4? The take-home message here is that there are some issues with calcareous soils that affect phosphorus and these micronutrients. So let me give you an example. This is not uncommon in soils in the Western United States. How much calcium carbonate is there in the surface 6 inches of a soil with 2% free lime? So the top 6 inches of soil within an acre weighs 2,000 pounds, roughly. Okay, so that's expressed here. There's approximately 2,000 pounds of soil per acre in the top 6 inches of soil. And if that has 2% free lime, that equals 40,000 pounds per acre. It's a lot. In fact, if you did the math, that's 20 tons per acre. There's 20 tons of free lime or calcium carbonate in the top 6 inches with a soil that has 2% free lime. And I bring this to your attention for a number of reasons. When somebody says 2% free lime or 1% free lime, those numbers are not inconsequential. They are exorbitant, exorbitant. They're excessive. And when I think about this, and you've watched enough of my videos already, you know I'm Italian, last name Ippolito. You know what I say when I see these numbers? You know what I say? I say, Mamma mia, that's crazy. 20 tons per acre? You're never going to get rid of this. Mamma mia, go eat a pizza. It's not going to happen. All right. So I'm telling you the story. I'm giving you a prelude to the story behind calcareous soils and trying to reduce pH in these systems. It's practically impossible on a large scale basis. Think Mamma Mia. It's not going to happen. All right. So, management considerations. What can you do? What can you do? Right? You can avoid planting crops that are sensitive or require a low pH. For example, the picture in the bottom right-hand corner, this is iron deficiency in blueberry. This blueberry plant was grown in a soil that was above probably pH 6. I wouldn't be surprised if it was grown in pH above 7.2 in a calcareous soil. You can apply micronutrients with the fertilizer, with the bulk fertilizer. Oftentimes this works pretty well with zinc. It does not work very well for iron in calcareous soils. You can band apply phosphorus for crops, or you can dual apply phosphorus with nitrogen. So band applying, if you haven't learned about band applying, it's putting a band of fertilizer, in this case, phosphorus fertilizer, 2 inches down and 2 inches over from where you plant the seed. All right. It's a concentrated band, so that phosphorus doesn't have the ability to greatly interact with soil and be bound as calcium phosphates. And we do this for a reason in acidic soils or calcareous soils, because phosphorus loves to be loved. And if you can place it in a concentrated band, the plant might be able to see it to a greater extent than if you broadcast and fully incorporate it. The other management consideration is you can try to reduce pH. You can acidify this. I can tell you that it's not practical. It's not recommended on a large scale, and it's only recommended for small scale ag. If you're working in a raised garden bed that's calcareous, has calcareous soil, you can probably get away with this. But it's just not going to happen in large scale production agriculture. There's a two-step process to do this. You have to dissolve all the free lime, and you have to reduce the base saturation from 100%. You have to kick off calcium from the exchange sites. So in the example that I gave you on the previous slide, if you have to remove 20 tons of free lime per acre, you're going to add a lot of acid, and you're not going to be happy. I can tell you for a fact, you're not going to be happy. Your wallet is not going to be happy. And then to remove the 20 tons of free lime, that's fine, but you still don't change the pH because you have to remove the bases that are associated with maintaining the high pH. And those bases are calcium based typically, sometimes magnesium. So how do you do it though? I just want to share this with you just so you have this little nugget of information. You can use several types of acidifying agents. You can use elemental sulfur. Elemental sulfur works well, but it requires microbial activity. So this is not going to do anything for you in the late fall and winter and early spring months, because you need microbial activity to degrade or convert sulfur from the elemental form to sulfate. And you need moderate temperature, and you need adequate moisture, i.e. you need time. But it does work. This is how it works. You add elemental sulfur, it reacts with oxygen and water in the presence of microorganisms that convert this reaction from the left side to the right side, and you create some free hydrogen ions and sulfate. When you combine these two H hydrogens and sulfate, that's sulfuric acid. So you can generate some acidity from this. All right. And so 1 mole of sulfur releases 2 moles of hydrogen. You can see that in this equation here. It works. I think you'd be crazy to try to do this on a soil that has 20 tons of free lime per acre in the top 6 inches, but you could do it, but I wouldn't recommend it. You could use sulfuric acid. You could skip the middleman and go right to sulfuric acid. I could tell you, you probably won't be using concentrated sulfuric acid in an ag setting. It is by far one of the worst acids to work with in a lab, let alone out in the field. It is highly reactive to when introduced to calcium carbonate. You can add aluminum sulfate. The aluminum, when this material dissociates, the aluminum will undergo hydrolysis and create 3 free hydrogen ions. In fact, you have 2 aluminum, so it'll create 6. You could do the same thing with iron sulfate. It's going to take time. It's going to take time. So what do you have to do? You have to dissolve all the lime. So you could do a couple things. And I used to teach this in my class in the past, and I stopped doing this, going through a calculation on how to actually do this because it's totally impractical. You could determine the amount of lime present, and you could determine that on a mill equivalent basis. And then you could determine the amount of mill equivalents of sulfur to add to dissolve the lime. And if you had 20 tons of lime per acre, you're going to add a lot of sulfur. Or you could use this rough rule of thumb that it's going to take 3.2 tons per acre of sulfur for each 1% calcium carbonate in the top 6 inches. So this is going to take like in the example I gave you, if there's 2% calcium carbonate, it's going to take almost 6.5 tons of sulfur per acre. And even then, the only thing that does is dissolves the lime. It doesn't change the pH because you still have calcium on the exchange sites. So you need to add even more than 6.4 tons of sulfur per acre to make a change in pH. So this is why this is really impractical, okay? So let me share with you, here's another example to tell you and drive home the point that this is impractical. It's impractical on a large scale basis. Let's say you have a soil with 5% lime. It's not uncommon in the Western United States. 5% lime times 3.2 is going to cost you, or it's going to require 16 tons of sulfur per acre. The price of sulfur for last year was $400 a ton. So 400 times 16 is what? A lot. 400 times 16 is $6,400. That's per acre. What if you had 500 acres? That's going to cost you a lot of money. I'm not going to tell you the number, but it's a lot of money. You're going to go bankrupt. Do the math. All right. And that only neutralizes the 5% free lime. And you still would have 100% base saturation, meaning all the sites on the exchange sites of the clays are filled with basic cations, primarily calcium, because you just dissolved all the calcium carbonate. And where does the calcium go? It went on the exchange sites. You still have to remove the calcium from the exchange sites. So you still need to reduce the base saturation. And that's dependent on the CEC and that pH versus base saturation diagram that you saw in one of the previous videos. So that's why this is definitely not practical on a large scale basis. If you have a high pH, you're dealing with a calcareous soil, you change the variety, you change the crop. Man, where I used to live, they planted houses. They grew really well in calcareous soils. Go figure. So, what are your options when you deal with a soil problem like this? Change the crop, change the variety, or you change the soil, such as what they did in this picture that I share with you in the introductory material for this class. If you knew that this site was calcareous to begin with, and you wanted to grow something that just did not like a calcareous soil, you would change the soil. Right? That's what the people did. The ancient Peruvians did in these moray circles. I'm not suggesting you do that. That's pretty extreme, but I hope that drives home a point that if you want to do something drastic with a calcareous soil, you have to do something very drastic and it's going to cost you. And that brings us to the end of Unit 3. If you have any questions, reach out.